Is it visible? Okay, just wait for 1 minute. So this was observation that if R is a ring, P belong to spec R if and only R mod P an integral domain. The similar result is using this theorem we found the spectrum of R mod I. So using this theorem, similar theorem, sorry, there is yes. R be a non-zero ring. M belongs to max spec, that is maximal ideal. R if and only if R mod M is the field. Proof. Suppose suppose M max spec R. We have to show that R mod M is a field and A plus. So have I defined what is field? No, I have not defined, right? What is field? So I have to define what is field. All of you know although what is field, but I need to define what is field. Let R plus dot be a commutative ring. All rings are commutative, but I mention it here. R is said to be a field if each A belongs to R minus 0, it has a multiplicative inverse. Note that a field is always the integral domain. A field is always an integral domain. Thus, AB equals to 0, A non-zero, A inverse belongs to R, so A inverse B equals to A inverse 0 equals to 0. B equals to 0.
This call is now being recorded.
But converse is not true. An integral domain may not be a field. Example Z. What is true? That a finite integral domain is a field. We'll prove that later. Now back to this theorem. Suppose M belongs to M is a maximal ideal. M belongs to max spec R, and A plus M not equals to 0 plus M. That is a non-zero element in R model. We need to show that it has a multiplicative inverse. Now, this implies A does not belongs to M. So, M plus A generated ideal is R by maximality, as M strictly contained in plus A generated, because A does not belongs to M. Therefore, it is strictly containment, and M is maximal. M is the maximal ideal, so this has to be R. Is a maximal ideal, so M plus A has to be R. So this implies 1 belongs to M plus A. So we can write 1 is X plus AB, where X belongs to M. So we can write 1 minus AB belongs to M. This implies 1 plus M equals to AB plus M equals to A plus M, B plus M. So A plus M is a unit. This implies R mod M is a field. Conversely, if R mod M is a field, we need to show that M is the maximal ideal. Suppose conversely, let wave field. Suppose M is contained in I. Strictly contained. So I need to show that I is R. So there exists A that belongs to M, but this is strictly contained in it. So there exists A belongs to I such that A does not belongs to M because it is strictly containment. So A plus M. This implies A plus M is a unit. This implies A plus M, B plus M, 1 plus M. For some, B belongs to R. This implies AB minus 1 belongs to M, that is subset of I. So now AB belongs to I as A belongs to I. This implies 1 belongs to I. Hence, R equals to I. We are done. So one line corollary is max spec R is subset of one line corollary is data. Let M belongs to Shaker. This implies R mod M is a field. Now a field is always the integral domain. I should write in it is in color con I don't know how to color it. Oh, this is good. So R mod M is an integral domain. M spec R. Now, question is, if R is in as I define polynomial ring. Let R be a ring X, a symbol called indeterminate. Consider the set x to the power I belongs to natural number union 0, where x to the power 0 is 1 R. Now, Rx is the set of A0 plus A1x span of this, like an x to the power n. I should write another way, not an. This is better notation. A0 such that AI belongs to R. These are called coefficient. These are just formal sound, just symbol. And uh, for range 1 lesser 0 lesser equals to I lesser equals to n, and n varies natural number. If so, I want to make it as a ring. Rx cross Rx to Rx define class an plus a0 x to the power n bm plus 0 x to the power m goes to an plus bm. That is another problem. Okay, this is m x n greater equals to m or greater than m, I write, because equality case I have already taken. And obviously product is here like Cauchy product dot this is where Ci is a summation b n minus k, that is k equals to so I should write here 1 degree b a n b n minus m minus 1. So I should write here in my notation a n a b minus s. S plus k is I. That is better. Cauchy product. So check that Rx plus dot is the ring. Example, indeed, uh, no, equality. Before checking that, I need to define equality. What is the relation? This is the unique expression. Two polynomial. This is uniqueness of expression. This is definition, okay? Px and Qx are said to be same if Px is your an plus A0 x to the power n, and that is Bm B0 x to the power m, where A0 not equals to 0, B0. Okay, I write it this way. M equals to n and M equals to n and AI equals to BI for all I. Okay, these are two non-zero polynomials. Or Px is zero polynomial if and only if equivalently Px is zero polynomial if and only if all coefficients are zero. Okay, Px equals to 0, all coefficients are 0. Now check that this is a ring, and moreover, if K is a field, then Ax is a vector space over K spanned by the set x to the power I belongs to natural number union 0. This is a basis. Not only this, and this is also linearly independent, spanned by the, and this guarantees element of this element of Rx or K, if we put Kr equals to K of the form this guarantees this is span of Rx is or Kx is that Xi, and this definition Px equals to 0 if and only if the all are 0 will gives you that it is a linearly independent set by the linearly independent set so if it is a K is a field, then it is a vector space over K. Now if it is if R is not a field, a ring, we'll see that it is a free module, free R module. That concept will be developed later. Okay, any question? Next we want to compute something. Then if R
Excuse me, the other point, sir.
uh,
If we our ring R was always commutative,
yes,
so can we define R? I mean, for any ring R with unity, or I mean, can we define the polynomial ring Rx for any ring R? I mean, our R was commutative always, but can we define it? I mean, can we do the these things for any ring? Or
you can define it. Okay, from coefficient. Now problem is that how to uh, mm, uh, what is the ideal structure? That is the problem. Okay, so another thing I have to mention, there is an ring homomorphism R to Rx inclusion map. A goes to A. This is a ring homomorphism because the definition of sum and product. দুটো যদি if two polynomials are constant, then just constant term will get sum. So it is ring homomorphism. Check that. You have to check that the inclusion map is a ring homomorphism. Okay, so it is injective, so I write this notation. Next question is, if R is question, if R is an integral domain, then Rx also. If R is a field, then Rx also field.
No, not if R is a field, then Rx need not be field.
Why?
If uh,
Your answer is right. Now why?
uh, actually, if R is a field, I mean, for Rx to be a field, it for every fx belonging to Rx, fx has to admit inverse in fx.
Fx
Sorry,
non-zero.
in Rx. But in that case, the set of all units in Rx is the set of all non-zero polynomials. I mean, the set of units
No, no, no.
in if.
Just say that X has no inverse. If I take Kx, if X has inverse, suppose you have done this, you need this. Okay, if R integral domain, then Rx also. You need this, you will need this. Okay, suppose X has inverse. So X into some Fx should be 1. Now, degree of F and degree of X will get plus, because Rx
Since
integral domain, and this is your multiplication rule. So what is C0? C0 is A0, B0. A0 non-zero, B0 non-zero. So A0, B0 non-zero. So degree will get plus in integral domain. Okay. So if R is integral, K is field, so K is integral domain also. So degree, this is degree of 1 is 0. So, and this is 1. 1 plus it is, I don't know, it is n. So n plus 1 contradiction. Okay. So X has no inverse. Your answer also right, but don't want to use many results, so many results that units of R is units of Rs equal. Okay. Simple, we approach in simple way. In later, we'll go to in integral domain, we'll go through that Euclidean domain, PID, UFD. So similar question will arise that if R is Euclidean domain, then Rx is also. If R is PID, then Rx is PID. If R is UFD, then Rx is UFD. So similar question. Okay. We'll answer all things. So right now it is not question, I want to prove. Okay. Is it if and only? Can I say this?
Sir, is R at the outset is R uh, commutative here? I mean, if in this statement,
All are commutative. Rings are commutative. In my first note, I assume that rings are commutative. Note this is, we restrict this green statement. Every day uh, we will uh, we will discuss only commutative ring. This note ring means commutative ring with identity. Okay, now answer your question. If R is integer, is it if and only if? Try.
yes.
Okay, it is true. It is if and only if statement.
Sir, is there any non-commutative ring R for which Rx is commutative? I mean,
No, no, no. Because R is a subalgebra of Rx. If R is non-commutative, then R is, how can be Rx is commutative? Uh, we will not discuss here any non-commutative things. Otherwise, it will get confused. This note only for commutative rings with identity, not only commutative ring with identity. If you have question right now, question for commutative ring. Next, when I study some non-commutative ring, there is some application also for non-commutative ring. For example, derivation module is non-commutative. G modules, well algebra, they are not non-commutative, and they this theory is also huge application. So, but right now I will discuss. I focus only on commutative. Okay, this part. Let fx equals to a0 plus I write this notation because of multiplication easier. Otherwise, here I defined this multiplication. I have to write n minus k m minus s type. This is problematic. But this notation also has some use whenever I talk with homogeneous something. Later you will see. Okay. Let fx belongs to Rx. If fx is not a zero divisor, that is, there exists no gx Rx minus 0 such that fx gx equals to 0, then we are done. If fx is a zero divisor, then z is gx belongs to Rx collection such that Rx minus 0, gx non-zero. minus 0 such that fx gx equals to 0. Take n equals to, I consider w equals to n such that degree degree gx as the gx belongs to z. Now I have not defined what is degree. Degree is the maximum power. Okay. If n is not 0, then degree of fx is n. Okay. This is the maximum power of x to the power I that occurs in fx. So W is a subset of natural number. So by well ordering property, it has a least element. And it is non-zero, non-empty set because it is a zero divisor. W subset of natural number union 0, because it can be happen that it is degree dx is 0. So and W is non-empty. Well ordering property, W has a least element. Let say M. Let Gx, or I write Hx better. Hx be the corresponding polynomial of degree M. B0 plus be the corresponding polynomial in Z. What is this? Okay. So Hx has degree M, so Bm, since degree Hx M, so Bm not 0. Now fx into hx is 0 because h belongs to z. Z is the collection of those polynomials such that fx gx is 0. So what is this? So an, what is fx? An x to the power n, bm x to the power n plus m plus lower degree term equals to 0. So an bm equals to 0. And now an not equals to 0, bm not equals to 0. And R is integral domain. So I write here in, so I take fx belongs to Rx, so it has a degree, n may be 0. So a non-zero polynomial. So I have to write reverse, it is a non-zero polynomial, obviously. So it is a non-zero polynomial, so it has a degree. So n may be 0. R is an integral domain. Contradiction. So Rx, so fx has no zero divisor, that means z is empty. Fx has no zero divisor. Hence, since fx is chosen arbitrarily, hence Rx is an integral domain. Note that observation if R is an integral domain, then and fx gx belongs to Rx, then degree fx gx equals to degree fx plus degree gx. Check. Okay. So next, note that if A is a field, then Ax is an integral domain. Because K is a field, it is integral domain, but it is not a field. An integral domain, but it is not a field. Note that X belongs to Kx and X is non-zero, has no multiplicative inverse, as if fx into x equals to 1 for some kx, then by the previous observation, degree fx plus degree x equals to 0, because the degree of 1 is 0, but this is 1, contradiction, and degree of x is positive or 0, so contradiction. Okay, any question? uh, this- Next, definition. Let R be a ring, then Jack R is intersection of M. M belongs to max spec R. Is called intersection of all maximum ideal is called uh, Jacobson radical, is called Jacobson radical of R. Okay, since observation, since max spec max, R is subset of spec R, we have intersection of P belongs to spec R. This set has much element, so intersection will get less. And that is equals to nil radical of R or root 0, and that is Jacobson. So nil radical is a subset of Jacobson radical. Okay. Next observation, let R be a ring. Ring means here always commutative ring with identity. There is no another ring. Let R be a ring. Then units of R equals to R minus union of M. M belongs to max spec R. So union of maximal ideal complement is units of R. Okay. So how to prove? Let proof. Let U, or I write small u, belongs to R be a unit. If so, there exists V belongs to R such that UV equals to 1. If U belongs to M for some M max spec R, this implies UV belongs to M by properties of ideal. 1 belongs to M, contradiction, because it is the maximal ideal. So it is proper and maximal. By definition, M is proper. So U does not belongs to for all M belongs to, this simply U belongs to, I want to write U, R minus union M, M belongs to max spec R. Next, suppose A belongs to R is not unit. This implies 1 does not belongs to A generated ideal, and that is what AX, such that X belongs to R. Because if 1 belongs to A generated ideal, then AX is 1 for some X. That means A is unit, contradiction. It's a proper, so A, it is a proper ideal. By the property of maximal ideal, that is the theorem, maximal ideal exists. Okay, by John's lemma. Since R is commutative ring with identity, here all rings are commutative. By properties of maximal ideal, there exists maximal ideal such that every proper ideal contained in some maximal ideal, maybe it is equal, but subset. That means now A belongs to A, because A can be written as A into 1, subset of M. So this implies A belongs to union of M. This implies A does not belongs to R minus union of M. So if it is not a unit, then it does not belongs to here. So counterpositively, we have proved. Okay. So units of R is R minus union of maximal ideal. So if it is R is a local ring, definition, what is a local ring? It is only one maximal ideal. Recall, a ring is said to be local if it has only one maximal ideal, and a ring is said to be a semi-local ring if it has only finitely many maximal ideal. So in a local ring, there is only one maximal ideal. So in a corollary, if you do it is smaller. If R is a local ring, so notation Rm for a local ring, M is the unique maximal ideal. Okay, so if Rm is a local ring, that means M is the maximal ideal. So local ring, then maximal units of R equals to R minus M. Now, question is, what is an example of a local ring? Can you construct a local ring? Please give me an example of local ring which has only one maximal ideal. A trivial example is a field, but I am not interested in any field. Any question? Give me an example of a local ring. That means give me an example of a ring which has only one maximal ideal. Hmm? Okay. Homework. Find spec z mod nz where n equals to p1 to the power alpha 1 to the power alpha k, where It is a prime decomposition. Here is a prime number. From here, at first you compute this. What is this? What are the prime ideals? You use obviously use this theorem. Uh, not this, not this. This theorem. How to find spectrum of R mod I. Okay. Using this theorem, you find what is spectrum of Z mod NZ, where P n equals to P to the power alpha 1 dot dot P to the power alpha k. Now you will see that how many prime ideals are there. Okay. Now next, conclude that any prime ideal in Z except 0 is a maximal ideal. Any prime ideal, any non-zero prime ideal is a maximal ideal. Then you calculate how many maximal ideal are there. Now try to characterize n such that it has only one maximal ideal. Then use this idea to any ring, not on only in Z. Okay. This is homework. Next day we will discuss from here. Okay. Any question? If you have any question, please ask me. There is a uh, useful theorem called prime avoidance. We'll do this next class. Okay. So if you have no question, then I'm leaving.